class, welcome to our introduction knowledge academy. The main aim of this lecture is discuss about the we can say semiconductors. Some important points regarding the semiconductors in a very, very detailed manner. So if you like the content of the channel, then please to like, share and subscribe to the channel and don't forget to press the bell icon button. So whenever we upload new video, the direct notice comes from the if any information in our lectures, and please open the comment section. We will definitely link to all those videos in the comment lectures. So why do we start up? So let's get started. So basically here, see what are the group 3 elements? Group 3 elements are nothing but these are called as a trivalent integrators. Because why these are called the trivalent integrators? Because they are going to have the, so whatever the elements which are going to present in this group 3 elements, they are going to have the 3 electrons in the valence of group. That is the reason we say these are the trivalent integrators. So what are the aluminum in this group 3 elements. So these are elements which are going to present the group 3 elements. So all these the elements basically they are going to have the 3 valence electrons, 3 electrons in the valence orbit. So because of this reason only they say these are the trivalent impurities. So if you try to add these impurities for a pure intrinsic semiconductor, then we are going to get a free type of semiconductor because we have one vacancy in the present in the valence band. So each atom is going to contribute one vacancy in the valence orbit. So we say these are the acceptor atoms because they want one electron and not to become orbit configuration. So that is the reason these are also called as the acceptor atoms. So group 3 elements are also called as the acceptor atoms also we can call. For acceptor elements also we can call. Now what are the group 5 elements? Group 5 elements are nothing but these are called as a pentavalent integrators. Pentavalent integrators because these elements are going to have the 5 electrons in their valence orbit. So that is the reason these are also called as a pentavalent integrators. So what are those elements in the group 5 which are phosphorus, arsenic, lead and bismuth. So these are the elements which are basically present in the group 5 elements of the we can say table. And so whenever you try to add these group 5 elements to a pure semiconductor, you are going to get a n type of semiconductor. Why means whenever you try to add this one, by default one extra electron will be always going to present the conduction band by default. So because of this reason only, we can say it is going to have one electron. Means the majority carriers are the electrons. So because of this reason, we say it is a n type of semiconductor. So in the case of p type of semiconductor, the majority carriers are the holes and the minority carriers are the electron. Whereas in the case of the n type of semiconductor, we are going to get the majority carriers are the electrons and the minority carriers are the holes. So whenever you try to add the group 3 elements for the pure semiconductor, we are going to get the p type of semiconductor. The majority carriers are the holes and the minority carriers are the electrons. Whenever we try to add the group 5 elements for the pure semiconductors, we are going to get the n type of semiconductor and the majority carriers are the electrons and the minority carriers are the electrons. Okay, the majority carriers are electrons and minority carriers are the holes. So majority carriers are electrons and minority carriers are holes. And what are the semiconductors? Group 5 elements are called as semiconductors. They have in the valence orbit they are going to have 4 electrons. So that is the reason they are called as the semiconductors. So for group 4 elements, what are the group 4 elements like silicon, germanium? All these are called as the semiconductors. They belong to group 4. Okay? So now the other concept which is the expression of the conductivity we'll try to discuss. This is another concept which is the expression of the conductivity. What is the formula? J is equal to sigma into E. J is equal to sigma into E. This is called as the Ohm's law in the field theory. Okay? And V is called here is called as the Ohm's law in the case of the electrical circuits. J is equal to sigma into E is called as the Ohm's law in the case of field theory. Okay? So J is equal to sigma into E. And what is sigma? Sigma is equal to N into E into U. J is called as the conductivity. Sorry, J is called as the current density. Sigma is called as the conductivity. And E is called as the electric field. N is nothing but charge carrier concentration. Here this is now with the numerical value it is equal to 1.6 10 to the power minus 19. U is the mobility. And I want to tell you an important point. The substitute the value of sigma in this equation, what are going to get? J is equal to N into E into mu into E. Because of substitute the value of sigma in this equation, so I have got this one. And I already told you the difference velocity is equal to mu into E. What is difference velocity? It's the product of the mobility into electric field. So difference velocity is the product of the mobility into electric field. So what is going to get? N into E into VV. So in the case of semiconductor, whatever the current that we are going to produce is because of the current due to electrons as well as V2 holes. So that in the same fashion, the current density is also because of both the current density due to electrons as well as V2 holes also. So therefore, the net current density is equal to the current density due to electrons as well as current density due to holes. So now I want to use this formula. So what this formula I want to basically use this one. So therefore, what you are going to get here? J means right here Ne into E into U into E plus NH into E into UH into E. As you can see clearly from this one. Okay? In place of N, I am taking Na here. In place of U, I am taking U here. For this one, in place of N, I am taking NH. In place of U, I am taking UH. So now, in these two terms, like triple is constant. So I take it outside. It's a common thing. So I take it outside. So we are going to get like this. Now what I will do? I will divide J by E. J by is nothing but current density. J by is equal to current density. Sorry, electrical conductivity. Small fraction here. J by is nothing but electrical conductivity. So overall electrical conductivity is equal to sigma is equal to J by E. So into J by E, what we are going to get? Ne into E into mu plus NH into E into UH. So this is what we are going to get. So some books, what they are going to use the notation Ne. Sometimes they use that N. Sometimes NH they use P. Sometimes they use Ne as UN. Sometimes they use mu as the UN. Sometimes they use UH as VP. So different the way of writing different notations. What is Ne or N? The concentration of the electrons. What is mu or UN? The mobility of the electrons. What is NH or P? The concentration of the holes. What is VH or VP? Is the mobility of the holes. Okay. So now, if you see these two things, E is a common thing. So if I take it outside, so E into N into mu plus P into VP. Okay. So this formula always you have to remember because a very very important formula. There are a lot of questions based on this formula. So you can say here, what is Ne or N? I'm only to this electron concentration of the. We can say the charge density. So based on number of electrons are going to present per unit volume. So the unit is 1 by meter cube. What is NH or P? It is concentration of the whole charge density. And this unit is 1 by meter cube. Means this one number of moles are present per unit volume. So 1 by meter cube. E is the amount of the charge of the particle. And its volume is 1.6 10 to the power minus 19. What is mu or mu? Just the difference. They are different relations, but the concept is same. Which is for the mobility of the electron. And its unit is meter square per volt second. What is mu or Vp? It is called as the mobility of the holes. And its unit is meter square per volt second. Sigma is for the conductivity, and its unit is 1 by 1 meter or mho per meter or Siemens per meter or 1 meter whole inverse. So there are different types of things. Okay? So we can use either mho per meter also we can use. And always the mobility of the electron will be always higher than compared to the mobility of the hole, because for a unit electric field, if you try to apply, the velocity of the electrons will be very higher than compared to the velocity of the holes. So because of this reason only, the mobility of the electrons will be very very higher than compared to the mobility of the holes. Means suppose if you are going to apply unit electric field, and the unit electric field, the velocity of the electrons will be very higher than compared to the velocity of the holes. So because of this reason only, I can say that the mobility of the electrons will be very very higher than compared to the mobility of the holes. So here what you have been, in place of Ne, you can write either Ne or N. In place of mu, you can even write Un also. In place of NH, you can write P. In place of UH, you can write Vp. Different notations. Here sigma is for the conductivity, J is for the current density, P is electric field, N is the electron concentration, and U is the electron mobility, and P is the concentration of the holes, and Vp is the mobility of the holes. Okay? So this is a formula I request you to remember. So always the electron mobility is always greater than the hole mobility, or you can say the mobility of the electron will be very very higher when compared to the mobility of the hole. So I request you to remember this formula. The next concept is the mass action law. So I will try to do this concept in a very simple fashion. The only to what is the value of N is the electron concentration is this one number of electrons are going to present per unit volume. What is for whole concentration of this one number of holes are going to present per unit volume. N is the intrinsic concentration, and these are this one number of charge particles which are going to present per unit volume. Na is called as the acceptor concentration, means this one number of acceptor atoms that are going to present per unit volume. Nd is called as the donor concentration means this one number of donor atoms which are going to present per unit volume. I have already told you acceptor atoms are nothing but group 3 elements. What are the donor atoms which are the group 5 elements? Okay, I have already told you acceptor means group 3 elements, donor means group 5 elements. Okay, so here I will give you some equation which is valid for both the intrinsic semiconductor as well as the extrinsic semiconductor. So I am going to give you an expression. It is valid for both the intrinsic semiconductor as well as the extrinsic semiconductor. Intrinsic means pure type of semiconductor. Extrinsic means whenever you try to do the doping the intrinsic, then you will get the extrinsic. Okay. So now the formula is, you have to remember this one, which is N into P is always equal to Ni square. N into P is equal to Ni square. Okay. N into P is equal to Ni square means, see, Ni is also a function of temperature. What is the relation? Ni square is always directly proportional to temperature Q. Okay. Ni square is directly proportional to temperature Q. Suppose if temperature increases, Ni is also increases. Okay. So therefore, suppose if I assume T is equal to constant, then Ni is also constant. So if Ni is constant, Ni square is also constant. So therefore, I can say that at constant temperature, the product of the electron concentration and the hole concentration is always constant. So remember this one. Whenever at constant temperature, the product of the electron concentration and the hole concentration is always constant for both the intrinsic semiconductor as well as the extrinsic semiconductor. So let's remember, which is Ni square is always very proportional to P cube. So as temperature increases, Ni increases, if temperature decreases, Ni decreases. But at constant temperature, Ni is constant. So therefore, at constant temperature, as Ni is constant, so therefore, at constant temperature, the product of the electron concentration and the hole concentration is always constant. It is valid for both the intrinsic semiconductor as well as the extrinsic semiconductor. Okay. So this is a very important thing. Always you have to keep in mind. N into P is equal to Ni square. So now we will do the analysis for the intrinsic semiconductor. First we will do the analysis for the intrinsic semiconductor. In the case of intrinsic semiconductor, the number of electrons will be always equal to number of holes. Electron concentration is always equal to hole concentration. So electrons are always going to be present in the conduction band and holes are always going to be present in the valence band. So okay, the electrons are always going to be present only in the conduction band and the holes are always going to be present in the valence band. So in the case of intrinsic semiconductor, always I can say that electron concentration is always equal to hole concentration. But so let me assume is a first equation. And I already told you what is the basic equation. N into P is equal to Ni square. I already told you that. So this equation is valid for both the intrinsic as well as extrinsic. So I am using in the case of intrinsic. But what is N? N is equal to P, substitute. So P into P is P square. So P square is equal to Ni square. So 2 cancels. What we are going to get finally? P is equal to Ni. So this is the second equation. So by seeing the first and second, what we are going to get? N is equal to P. So P is also equal to Ni. So therefore finally what we are going to get? N is equal to P is equal to Ni. So this is a wonderful equation in the case of the intrinsic semiconductor. So therefore I can say that in the case of intrinsic semiconductor, the value of N is always equal to the value of P, and the value of P is always equal to the value of Ni. So therefore that electron concentration is always equal to hole concentration and both are equal to intrinsic concentration. And I already told you what is a electrical conductivity formula. Just now we discussed that sigma is equal to E into M U plus P mu T, which just now we discussed. Suppose if I want to write this equation for intrinsic semiconductor, how will I write? Suppose if I want to write this equation for intrinsic semiconductor, then what? Then how can I write? N is equal to Ni, P is also equal to Ni. As you can see, clearly both are equal to Ni. So in case of N, I will write Ni. In case of P also, I will write Ni. So then I can take Ni common outside. And what we are going to get? Ni into E into U1 plus mu P. So this is a simplified expression of the conductivity in the case of the intrinsic semiconductor. So this is a general expression. This is a general expression. But if I want to write this expression only for the intrinsic semiconductor, so in the case of intrinsic, as you can see clearly, N is equal to P is equal to Ni. So in case of N, I will take Ni. In case of P also, I will take Ni. So take Ni as a common. What we are going to get? Sigma is equal to Ni into P into U1 plus mu P. So this is a very important formula we have used in the case of the intrinsic semiconductor. So now we will do the analysis for the eccentric. In the case of the eccentric, we have two things. One is the P type and the other is the N type. So first I will go for the P type semiconductor. See, I've already told you in the case of PDF semiconductor, the holes are more when compared to electrons. The holes are more when compared to electrons. So holes are the majority carriers and the electrons are the minority carriers. So what are the number of hole or hole concentration is equal to? Basically, in the case of P-type, as we're adding the group 3 elements, so definitely group 3 elements are nothing but acceptor atoms. So whenever you try to add one acceptor atom, by default there is a one hole in the valence band. So if we add any number of acceptor atoms means by default we are going to have any number of holes in the valence band. So any number of holes by default they are going to be present. And also extra thing is also going to be present because of the natural semiconductor. See, P-type is nothing but it's basically eccentric. Yes. When you add a doping, then only it is become eccentric. But initially, there are some holes are there. Initially, before you do use of doping, because of temperature, there is some type of holes. So that is because of the that is because of the thermal temperature. Initially, because of intrinsic semiconductor. So these are the Na is nothing but these are number of holes which are present because of doping. These Na number of holes are present initially before doing doping only. These are present already. But after that, we are doing a doping, right? So this one number of holes are present in the valence band because of doping. So any number of holes are present because of doping. Na are already present in the material because previously it is intrinsic. Okay? So this is the overall number of holes which are going to present. And I already told you what's the basic equation which is valid for both the intrinsic and eccentric, which is N into P is equal to Na square. So I know the value of P, so I want to get the value of N. So N is equal to Na square by P. P value is Na plus Na. So substitute Na square by Na plus Na. And I say always Na will be very high when compared to Na. Yes, the concentration of the acceptor atom should be very high when compared to intrinsic concentration. So because of this, what is going to happen? Na is equal to this, so I can make it different. So in the formula for Na, please be very I don't talk, so I can make the question. So finally, N is approximately equal to Na square by Na. So N is approximately equal to Na square by Na. So therefore I can say this is the whole concentration in the case of the P-type semiconductor, and this is the I can say electron concentration in the case of the P-type semiconductor. Okay. Now let's go for the N-type of semiconductor. See, N-type semiconductor means whenever we try to add the pentagon impedance for the two semiconductor, we are going to get the N-type of semiconductor. In the case of N-type of semiconductor, the majority carriers are the electrons and the minority carriers are the holes. So therefore, what you are going to get now? See, right? See, whenever you try one donor atom, by default we are going to get one free electron in the conduction band. Suppose if we add any number of donor atoms, then we are going to get any number of electrons in the conduction band. So by default, we are going to get any number of electrons because of the doping. But before doing the doping, it is intrinsic. So because of the temperature, thermal energy, because of temperature, some of the electrons are going from valence band to conduction band. So how many electrons are nothing but Na? So Na. So Na is nothing but because of the intrinsic nature, because of the intrinsic semiconductor, before doing the doping. And Na after doing the doping. So Na number of electrons are available in the conduction band before doing the doping, and any number of electrons are going to available in the conduction band after doing the doping. Okay, very important thing here. What is Na? Na is nothing but these kind of number of free electrons. These kind of number of free electrons are going to occur in the conduction band before doing the doping because of thermal energy. And Na is nothing but I can say after doing the doping, these kind of number of electrons, free electrons are going to available in the conduction band. So we do a summation. So overall, we are going to get this number of electrons which are going to present in the conduction band, which is N. Okay. So now, what is the basic equation that is valid for both the intrinsic as well as the eccentric, which is N into P is equal to Na square. So I know the value of N, but I want to get the value of P. P is equal to Na square by N. N is nothing but ND plus N. Have substituted. So always ND will be very higher when compared to N. Means the donor concentration will be always higher when compared to the intrinsic concentration. So because of this, what I can say that ND is very high when compared to Na. So I can get the Na here and also here. And what you are going to get? N is approximately equal to ND and P is approximately equal to Na square by ND. So N is approximately equal to ND and P is approximately equal to Na square by ND. Where N is nothing but the electron concentration in the N-type of semiconductor, and P is the whole concentration in the case of the N-type of semiconductor. Okay, this is a very important concept that you need to remember. Okay. So So the next concept I will try to tell you, which is about some important relations that we have to remember in the case of the semiconductors. The next speed is equal to A naught into T cube into A to the power of minus E G naught by K into T. It is the Boltzmann constant and T is the temperature in the I can say T is temperature in terms of Kelvin and Na is the intrinsic concentration. So as you can see clearly, Na is very proportional to T cube. Plus as temperature increases, intrinsic concentration is also going to get increases. As temperature increases, intrinsic concentration is also going to get increases. Means what is the meaning of this one? Suppose you take a pure intrinsic semiconductor and you try to increase the temperature around this intrinsic semiconductor, then by default, whatever the electrons which are present in the valence shell, they will move from valence band to conduction band. So by default, as the number of electrons in the conduction band increases, same number of holes also we are going to create in the valence band. So therefore, the charge carriers are increasing, right? So therefore, that is the reason as temperature increases, Na is also increasing. So as you can see clearly here. So this is the relation. Both are not only linear relationship, they are some non-linear relationship. But even though temperature increases, Na is increasing. As you can see clearly here. And also mobility. So mobility is having some relation with the temperature like this. U is that proportional to T to the power of minus E. So U is also, mobility is also going to depend upon temperature in this fashion. So this equation is going to be valid only for 100 Kelvin to 100 Kelvin. Okay? So mobility is also basically a function of temperature. As temperature changes, mobility is also going to be changes for both the electron as well as hole also. So it is basically a function of temperature. And this equation is valid only for 100 Kelvin to 400 Kelvin. So let me tell you another concept is the Hall voltage. So Hall voltage is a very important concept in the case of the semiconductor. Suppose let me take a small semiconductor material. I am taking a small semiconductor material. Suppose I am passing the current in this direction. So through the semiconductor, I am passing the current in this direction. In this direction, I am going to pass the magnetic field. Then what is going to happen? A voltage is going to get induced in the semiconductor. A voltage is going to be induced in the semiconductor. That is called as a Hall voltage. So in one direction, I have passed the current in the semiconductor. In the other direction, I have applied the magnetic field in the semiconductor. So then, because of these two things, overall, we are going to get some type of voltage in this semiconductor that is called as a Hall voltage. See, some concept I will try to explain. Suppose you take some electrical wire and you try to inject that one in the electrical wire and you try to keep that wire in the case of magnetic field, then a Lorentz force is going to be created on that wire. Same here also. In the semiconductor, you try to pass the current and in one direction and the other direction try to put the magnetic field. So because of these two things, the voltage is going to get induced. The charge particles, whatever charge particles which are present here, they are going to have some deflections. So because of that, what is going to happen? The voltage is going to get produced in this electrical, that is called the Hall voltage. So the semiconductor is having some amount of dimensions. As you can see clearly, there is a W dimension, there is a L dimension, and there is a D dimension. There is nothing but the height of the semiconductor. So as you can see clearly, this is the height of the semiconductor. Okay? L is nothing but there is a dimension of the semiconductor which is along the current axis. As you can see clearly, this is the direction of the current. So L is also in the same direction. So therefore, L is nothing but the dimension of the semiconductor which is along the current direction. And if you see W is nothing but it is in this direction. It is in this direction, and this is also magnetic field direction is also same. So therefore, W is nothing but the dimension of the semiconductor which is along the magnetic field. Whereas L is the dimension of the semiconductor which is along the current direction, whereas W is the dimension of the semiconductor which is along the magnetic field direction. So because of this, what is going to happen? See, the charge particles are going to present in the semiconductor. So whenever current is passing, what's the meaning of current? The charge particles are moving. The charge particles are moving. So because of magnetic field, there will be a force. Charges are moving and also you are going to keep the magnetic field. So definitely there is a magnetic force which is nothing but Q into Vd into B. That is a charge of that particle and V is the velocity and V is the magnetic field. Because you know the basic formula. The magnetic force formula is equal to Q into V cross of V cross. V bar plus V bar. Okay. After taking the magnetic value, so therefore Q into what is V? The drift velocity. We are going to know certain velocity, that is called drift velocity. So Vd into V. Okay. I will tell you. Q into Vd into V. Okay. Now, What is the Coulomb force? Coulomb force is also going to act on why means, see, some charges are going to have a magnetic force. So because of that, the charges will move downward. And the remaining charges also try to move. But already some charges are there down. So because of that, what is going to happen? The light just will get repelled. So there is some type of Coulomb force. That is a Q into E. So if this force, the net force is not zero, then until that time the charges will come down and they will accumulate on the surface of the semiconductor. If it is equal to 0 means no more further moving downward. Okay. So at steady state both will be equal. So I am going to equate these two equations. So finally QQ cancels. What you are going to get? E is equal to VD into D. Okay. E is equal to VD into D. And you know the current expression formula I is equal to N into E into A into VD. Okay. It's a basic formula. This you can see in the case of analog electronics there. I is equal to N into E into A into VD. I want VD. So VD is equal to I by N into E into A. You substitute the value of VD in this expression and if you simplify what you are going to get, E is equal to I by N into E into A into V. Okay. But you know, what is electric field formula? Electric field is equal to voltage by distance. Voltage by distance. So voltage is equal to electric field into distance. What is the voltage in Hall voltage? Right? So Hall voltage is equal to electric field into distance. D. E value, you know, this value, this formula, let's substitute I into B by N into E into D. And what is A? A is nothing but here, this area. The area which is perpendicular to current axis is called the area. What is A? A is nothing but the area of the semiconductor which is perpendicular to the current direction. What is A? A is nothing but the area of the semiconductor which is basically perpendicular to the current direction. So this is the area. So what is this length? This length is W and this length is D. So what is A? A is equal to W into A. So A is nothing but the area of the semiconductor which is perpendicular to current. As you can see, the current is perpendicular to this semiconductor area. So this is the area A. A is equal to this length is W and this length is D. So W into D is nothing but A. So A is equal to W into D. In case of A, I substitute W into D. So DD cancels. Finally, you are going to get W. So in case of A, I substitute W into D. So DD cancels. Finally, you are going to get W. So E into B by N into E into W. So this is the Hall voltage. If you see clearly, Hall voltage is directly proportional to current. It is directly proportional to magnetic field. It is inversely proportional to concentration of the charged particles and is inversely proportional to thickness of the semiconductor. W is nothing but thickness of the semiconductor, and W is always the dimension of the it's a dimension of the semiconductor which is along the magnetic field. Okay? This is a very important formula. There are a lot of questions based on this formula of the Hall voltage. I request you to remember. And the polarity of the Hall voltage is different for different semiconductors. Yes, it is a positive for the P type of semiconductor and it is negative for the N type of semiconductor. So the polarity of the Hall voltage is different for different semiconductors. Means it is positive for the P type of semiconductor and it is negative for the N type of semiconductor. So whatever this formula I have given from the N type of semiconductor, because here I use the majority carriers of electron, so I use the symbol N. Suppose if you want to derive the formula for the P type of semiconductor, instead of N, you have to write P, because in the case of P type of semiconductor, holes are the majority carriers. So in case of N, you have to write the P. So let me clear this concept. So whatever this formula, it is for the N type of semiconductor. In the case of N type of semiconductor, electrons are majority carriers when compared to holes. So that is the reason here I will take N. But if you want to write the formula for P type of semiconductor, in case of N, you have to represent the P, because in the case of P type semiconductor, holes are the majority carriers when compared to electrons. Okay. So that is the reason. So the Hall voltage is having a different polarity for the P type and N type. So for P type is positive Hall voltage and for N type it is negative Hall voltage. So what I want to do, what is A? A is nothing but area of the semiconductor is perpendicular to the flow of the current. I want to using this meter square. What is D? D is nothing but width or the height of the semiconductor. I using this meter. D is nothing but just a numerical value of the charge. It is 1.63 10 to the power minus 90. And what is N? N is nothing but the concentration of the charges, or we can say the charge densitiness. Is for number of charges are going to present in the unit volume. So what is the unit here? 1 by meter cube, or 10 to the power minus 3. What is VD? Drift velocity. I already told you. So drift velocity formula is nothing but mu into E. Mu into E. Okay, it's a very important formula. You have to remember. Where mu is the mobility and E is the electric field. What is it? It is nothing but the dimension of the semiconductor along direction of the current. As you can see clearly here in this picture, it is nothing but dimension of the semiconductor which is along the direction of the current. So what is W? W is dimension of the semiconductor, which is along the direction of the magnetic field. Okay. W is dimension of the semiconductor, which is along the direction of the magnetic field. I use this meter. See, you can see only the Hall voltage in the case of the semiconductors only you can see. Basically, you can see this Hall effect. You can see this Hall effect only in the case of the semiconductors. So it can be a P-type or it can be N-type. So you can see only this Hall effect only in the case of semiconductors, where it is a P-type or N-type. But you can't see this effect in the case of the conductors. Why? Why means in the case of conductors, you have lot of free carriers, you have lot of charge particles, lot of free electrons, because in the case of conductors, there will be a lot of free electrons in the conduction band. The value of N will be very high. If N is very high, then by default, its overall value will become very zero. So approximately zero. Therefore, in the case of inductors, I've already told you, there are a lot of free electrons you can see in the case of conduction band. So when is happening, the concentration of charges is very high. It's very huge value. So whenever the denote is very high, so overall value will become zero. So therefore, the Hall voltage is approximately equal to zero in the case of conductors. So that is the reason you cannot see the Hall effect in the case of conductors, but you can see the Hall effect in the case of semiconductors, but it is absent in the case of the conductors. As you can see clearly, because the value of the free electrons that are going to present in the conduction band is very high, very high. So because of that reason only, as the value of N increases, the overall value of the waveform decreases because N is present in the denominator. So the Hall voltage is approximately zero, means it is absent. The Hall effect is basically absent in the case of the conductors. And I already told you what is the Hall voltage formula, I into B by N into E by W. So this formula is applicable for the N type of semiconductor. Because in the case of N type of semiconductor, the majority carriers are the electrons, we are using the electron concentration as N. But in the case of P type of semiconductor, holes are the majority carriers. So therefore, in place of N, we have to replace N by P. That's it. The formula is same, only thing is, in place of N, we have to replace N by P. Okay. So this is the formula for the N type of semiconductor and this is the formula for the P type of semiconductor. So basically, Hall voltage polarity is different for different type of semiconductor. For P type it is positive and for N type it is negative. Okay. This is a very important thing that you need to remember. So let us discuss the next concept, which is called as the Hall coefficient. Okay. Hall coefficient is not, its notation is nothing but RH. Hall coefficient notation is nothing but RH. Okay. RH is called as the Hall coefficient. What is the formula of this one? It is the ratio of the E by J into B. What is the formula of this one? The Hall coefficient is RH. It is equal to the ratio of the electric field by current density into magnetic field. And I wanted to what is electric field, just now we have discussed. It is a product of the D, the drift velocity into B. What is the E is equal to drift velocity into B. By what is J? We just now we discussed N into E into VD. In the previous slide we can see clearly what is J, N into E into VD. And B, same thing everything. So here VD into B, then VD into B cancels. Finally we are going to get 1 by N into E. So this is for the N type of semiconductor. This is for the N type of semiconductor. Suppose if you are using for P type of semiconductor, means here in place of N, or the represent by P. So this is the formula for the N type of semiconductor, and this is the formula for the P type of semiconductor. Here N is the electron concentration and P is the hole concentration. So this is the formula for the N type of semiconductor, and this is the formula for the P type of semiconductor. Suppose if you know the Hall coefficient, what you can figure out? If you know the Hall coefficient, definitely E value is a numerical value. So if you know Hall coefficient and you know the value of P, then you can get the value of N, or you can also get the value of P. So whenever you know the value of the Hall coefficient, you can figure out the value of N or P. It is nothing but concentration of the charge particles. Yes, these number of charge particles are going to present per unit volume. Yes, we can also call it as the charge density. So you can even figure out the charge density, and also its sign also you can figure out. Why? Because electrons will have the negative sign and the holes will have positive sign. So for what you can figure out? So whenever you know the Hall coefficient, then you can figure out the value of N, or you can find the value of P. So another thing here are nothing but they are the charge carrier concentrations. Concentration of the charge carriers are the, you can say this number of charge particles are going to present per unit volume, or you can also say charge density also we can call. So therefore, whenever we know the value of the Hall coefficient, we can figure out the charge density as well as sign, because N is the whole electron concentration and P is the whole concentration. Electrons are negative and the holes are the positive. So therefore, we can even know the sign also. So that is the reason whenever you know the value of the Hall coefficient, you can figure out the sign as well as charge density, okay, of the carriers. So very, very important statement. Always you have to remember, whenever you know the Hall coefficient of a particular device and particular semiconductor, you can figure out the charge concentration as well as its sign also. Whether it is electron or whether it is a volts also, you can figure out with sign also, you can figure out. So therefore, whenever you know the Hall coefficient, you can figure out the sign as well as charge density of the carriers. Okay, very important statement. I request you to remember this one. And I've already told what is RH. See, it has basically some signs of the, see, all voltage is also having a sign as well as all coefficient is also going to have the sign. All coefficient is positive, but whenever number of volts are more than the number of electrons. Whenever the number of volts are greater than the number of electrons, means it is possible only in the case of P type of semiconductor. This is valid for the P type of semiconductor. Same thing in meter. So you can say the all coefficient is positive for the P type of semiconductor, because in the case of P type of semiconductor, the number of volts are more than the number of electrons. And the value of the RH is negative for the, so whenever the number of electrons are more than the number of volts. So the RH value is negative whenever the number of electrons are more than number of volts. So whenever electrons are more than number of volts, means electrons are more and volts are less, means it is nothing but N type of semiconductor. In the case of N type of semiconductor, electrons are majority carriers and the volts are the minority carriers. So therefore, RH value is negative. And RH value is equal to 0 when P is equal to A. Okay, P is equal to A. Because whenever the number of volts and number of electrons are equal, by default, the Hall coefficient is equal to 0. So this is a very, very important thing here. So you can see clearly here, I can say the RH value is basically, it is a positive when number of volts are more than number of electrons. So this is possible only in the case of the P type of semiconductor. And the RH value is basically negative only when the number of electrons are more than number of volts. This is possible only in the case of the N type of semiconductor, because in the case of N type of semiconductor, the electrons are majority carriers and the volts are the minority carriers. And RH value is equal to basically 0 when the number of volts is equal to number of electrons. This is possible only in the case of the intrinsic semiconductor. Okay. So therefore, you can say RH value is positive for P type of semiconductor, it is negative for the N type of semiconductor, and it is 0 for the intrinsic. Ideally, it is 0, but practically it is negative. I means listen carefully. See, ideally, its value is equal to 0. I only told you that because in the case of intrinsic, both the whole concentration and the electron constants are equal. So by default, ideally its value is equal to 0, but practically its value is equal to negative. I means very simple. Even though in the intrinsic semiconductor, the value of P is equal to value of N, but electron mobility is very higher when compared to hole mobility. So because of this reason, its value is negative. So because of the electron mobility is very higher when compared to the hole mobility. So because of this reason, its value is negative. So whenever in the questions if they are asking what is the Hall coefficient of the intrinsic, means always go for the practical value which is negative. Okay? Always go for the practical value which is negative. Don't go for the ideal value. Always go for the practical value. So what I can say finally, always remember these things. These final tips I try to tell you. So always remember this one. The Hall voltage as well as the Hall coefficient, both the things are positive for the P type of semiconductor. Okay, it is negative for both the N type as well as intrinsic. Okay, this is a very important thing that you always have to keep in mind. So the examinations they will ask you, what is the polarity of the Hall voltage or the polarity of the Hall coefficient for the P type of semiconductor? Is it positive? Whereas what is the Hall voltage or the Hall coefficient for the N type of semiconductor or the intrinsic semiconductor is by default you have to keep as a negative. Okay, so you go for the practical value. Don't go for the ideal value in examination. You go for the practical value. Ideally it is 0 only, but practically it is negative. So always remember this important thing. Whether the Hall voltage, so the polarity of the Hall voltage or the polarity of the we can say the Hall coefficient is positive for the P type of semiconductor. It is negative for both the N type of semiconductor as well as the intrinsic semiconductor. So very, very important thing you have to remember. What is the RH Hall coefficient? Okay. And what is E? E is electric field. J is the current density. What is B? Magnetic field. What is N? N is the carrier density or the charge concentration. Carrier density or the charge concentration is the number of charge particles which are going to present the unit volume. Okay. And this unit is 1 by meter cube. What is it? It's a numerical value which is 1.6 10 to the power minus 19. It's an amount of the charge of a given particle which is 1.6 10 to the power minus 19. Okay. So this is very, very important thing you have to keep in your mind. The next thing is here, we are going to discuss another concept is by using Hall effect, what we can determine. So with the help of Hall effect, we can determine these five things. So with the help of Hall effect, we can determine these 5 things, which are determined type of the semiconductor. So I already told you the polarity of the all voltage is different for P type as well as N type. But P type it is positive and for N type it is negative. So just by knowing the polarity of the all voltage, we can figure out what type of semiconductor it is, whether it is a P type semiconductor, whether it is a negative, whether it is an N type of semiconductor. So if you got the all voltage positive, by default it is a P type of semiconductor. If it is a negativeness, by default it is a N type of semiconductor. So therefore, by using the Hall effect, I can figure out the type of the semiconductor, whether it is an N type or whether it is a P type. So for P type, the all voltage is having the positive polarity and for N type it is having the negative polarity. And also with the help of Hall effect, we can also figure out the carrier concentration, whether it is here or whether it is P also. Yes? Whether it is an electron concentration or whether it is a hole concentration, also we can figure out. And also we can figure out the conductivity, which is sigma. And also we can figure out the mobility, which is mu. And also we can figure out the drift velocity Vd. So all these 5 parameters we can easily figure out with the help of the Hall effect. So I request you to go through all these 5 things. So whenever you know the polarity of the Hall voltage, we can figure out whether it is a what type of semiconductor. If the polarity of the Hall voltage is positive, it is a P type of semiconductor. If it is a negative, it is N type of semiconductor. And also we can determine the carrier concentration, whether it is a electron concentration or whether it is a hole concentration. And also you can figure out the conductivity of the material, sigma. And also you can figure out the mobility of the electron as well as hole. And also you can figure out the drift velocity, Vd. So all these 5 things you can figure out with the help of the Hall effect. Okay. So the next concept is here, thermal velocity of the electron. So thermal velocity of the electron, what is the expression of the thermal velocity of the electron, which is Vt. So basically, for a given electron, if you try to give the energy, definitely it is going to have some type of velocity. So as what is the kinetic energy of the electron? Half mv square, then V is something like Vt. So half mv square is equal to 3 by 2 into K2. Okay. This is a thermal energy formula. Okay. This is a kinetic energy formula and this thermal energy formula. So 3 by 2 into K2. So this is a kinetic energy of the electron is equal to thermal energy that we are going to give input. So input that we are going to give is thermal energy. That is basically converting into kinetic energy. So under ideal condition, both are equal. So 3 by 2 into K2. So 2 cancels. So try to get the value of Vt, which is Vt is equal to 3 into K into T by N. Where M is nothing but the mass of the electron. Okay. Where Vt is the thermal velocity of the electron and the K is for the Boltzmann constant and T is the temperature in always Kelvin. It is always measured in terms of Kelvin only. Where M is nothing but mass of the electron. And what is the P is called as the freedom, the degree of the freedom of the electron. So basically we have 3 axes. X axis, Y axis, and Z axis. So how many freedoms we have? 3 freedoms. The degree, how many degree of freedoms are there? 3. So therefore, basically we have 3-dimensional system. So 3 axes we have. X axis, Y axis, Z axis. So electron is having the degree of freedom is nothing but 3. So therefore 3 is nothing but this number of degree of freedoms are possible for the electron because we have X axis, Y axis, and Z axis. So therefore 3 is nothing but the degree of freedom of the electron because it can be either in X axis or Y axis or Z axis. So then there is a value of the 3. So Vt is equal to 3 into K into T by N. It's a very important formula that you need to remember. Now, one more important point basically I want to tell you. See, and here I've already told you NS is very proportional to TQ. This one I've already told you, right? In intrinsic concentration is always very proportional to temperature. So NS is very proportional to TQ. Here I have told you that whenever temperature increases, Ni will increase. I've already told you, right? So basically, if you see clearly, for the intrinsic semiconductor, so for the intrinsic semiconductor, what I told you, N is equal to P is equal to Ni, just now discussed, right? So suppose, listen carefully. Suppose if temperature is equal to 0 Kelvin, what is going to happen? If temperature is equal to 0 Kelvin, then definitely what is the value of Ni? N is also equal to 0 because if T is equal to 0, temperature is based in terms of Kelvin only. I already told you temperature is measured in terms of Kelvin. If T is equal to 0 Kelvin, then what is Ni? Ni is also equal to 0. So therefore, what I can say, in the case of intrinsic semiconductor, if you try to keep this intrinsic semiconductor in a place of 0 Kelvin temperature, so definitely Ni is equal to 0. If Ni is equal to 0, N is equal to 0. So P is also equal to 0. Means there are no charge carriers. There are no charge carriers in the conduction band as well as in the valence band. So no free electrons in the conduction band and no vacancies in the no holes in the valence band. When the charge carriers are purely absent, what we can say this is going to act like an insulator. That is the reason whenever you try to keep the intrinsic semiconductor in a 0 Kelvin temperature, this intrinsic semiconductor is going to act like an insulator. Okay. Now go for the P type of semiconductor. Suppose if you go for the P type of semiconductor connector, if you take this P type of semiconductor and if you try to keep in the 0 Kelvin, what is going to happen? At 0 Kelvin, Na is equal to 0. Yes, just now we have discussed if P is equal to 0 Kelvin, Na is equal to 0. But Na is there. So Na is there means P is not equal to 0. Means if P is not equal to 0 means what is the meaning here? Holes are present, right? So holes are present in the valence band. So charge carriers are present. Therefore, yes, even though you try to keep the P type of semiconductor in the at a temperature of 0 Kelvin, still the holes are present. So because of this one, what I can say that conduction will happen. It is going to act like a conductor. Okay? Now let's go about the N type of semiconductor. If you try to keep the N type of semiconductor in the 0 Kelvin, what is going to happen? At 0 Kelvin, Na is equal to 0. So if Na is equal to 0, Na is equal to 0, Nd is there still. So N is equal to Nd. Because what is the meaning of this one? If Nd is there, means some donor atoms are there. So because of that, electrons are charge carriers are all present in the conduction band. Some are there. So because of that, the conduction will still occur. So therefore, what it is going to act like a conductor. So what I can say finally, the very important thing always you have to keep in your mind, which is for whenever you keep the intrinsic semiconductor in a 0 Kelvin temperature, it is going to act like an insulator. Whereas when you try to keep the eccentric semiconductor, whether it is a P type or N type, if you keep this one in the 0 Kelvin temperature, it is going to act like a conductor. Okay, it's a very important thing. Always you have to keep in mind. I want to do the concept also. Okay, so whenever you try to keep the intrinsic semiconductor in 0 Kelvin temperature, it is going to act like a perfect insulator because there are no free charge carriers. Okay. Whereas if you try to keep the eccentric semiconductor, whether it is a P type or a N type, in the case in the 0 Kelvin temperature, but still the free carriers are present. So because of this, it is going to act like a conductor. So therefore, whenever you try to keep the intrinsic semiconductor in the 0 Kelvin temperature, it is going to act like a perfect insulator because there are no free charge carriers. Whereas if you try to give the eccentric semiconductor, whether it's a P type or N type in 0 Kelvin temperature, it is going to act like a conductor because of the free charge carriers are absent, present. Okay. This is a very important thing you need to keep in your mind. And how we do the concept with the help of these relations also, I will explain. Okay. So let me try to explain the other concept. So let me tell you a small concept here regarding the temperature progression and the resistance. So what is the temperature progression for resistance for different materials? I will try to discuss. So basically we have three types of materials. What are those? Conductors, semiconductors and insulators. Okay? Conductors, semiconductors and the insulators. I will try to discuss what is the temperature progression for resistance for these three materials. So conductor is always going to have the positive temperature progression for resistance. As temperature increases, resistance will also increase. Whereas in the case of semiconductors, we have two things based on the type of the doping. If we go for high doping, then we will have the positive temperature progression for resistance. If you go for the light doping, it will have a negative temperature progression for resistance. Whereas insulators will always have the negative temperature progression for resistance. Okay. So as you can see clearly, what's the meaning of positive temperature progression for resistance is as temperature increases, the resistance will increase. Okay. Negative is as temperature increases, the resistance will decrease. Okay. So now I will give you some important point here. So see clearly, based on the type of the doping, the semiconductors can have either positive temperature progression for resistance or negative temperature progression for resistance. You can see based on the doping of these semiconductors, you can have either positive temperature coefficient for resistance or negative temperature coefficient for resistance. As you can see clearly, so based on the doping of the semiconductor, we can have either a positive temperature coefficient for resistance or the negative temperature coefficient for resistance. Okay, it's a very very important thing. Okay, always you have to keep this one. Okay, so what is the best example of the light doped semiconductor? Which is nothing but thermistor. And what is the best example of the high doped semiconductor? Resistor. I give you also. So you can see what is the light doped semiconductor best example, thermistor, and what is the heavy doped semiconductor best example is transistor. So I already told you light doped semiconductor is going to have a negative temperature coefficient for resistance. It means that whenever the temperature increases, resistance will decrease. If resistance decreases, energy will increase. Heavy doped semiconductor, the best example is resistor. It is going to have the positive temperature coefficient for resistance. As temperature increases, the resistance will increase. If resistance increases, then conductivity will decrease. Okay, as you can see clearly here. So now, this is a very important thing you need to keep in mind. Okay, so this is a very important concept. What is the temperature coefficient for resistance for different types of materials when in a clear-cut manner? Suppose there is some other concept I will try to explain. Suppose some electrons are in a valence band, and if you want to move the electron from valence band to convection band, how you can move it? By giving some thermal energy to that electron. So whatever the energy that you are going to supply to the electron which is present in the valence band, if you give it an energy which is more than or equal to band gap energy, then only the electron can go from valence band to conduction band. So whenever you try to give thermal energy to the electron which is present in the valence band, if the energy is more than or equal to band gap energy, then only the electron can go from valence band to conduction band. So when E is greater or equal to Eg, then only that electron can go from valence band to conduction band. Okay. Then what is going to happen? If it goes from valence band to conduction band, and the free electron in the conduction band will increase. So because of that, the charge carriers will increase. So because of that, the conduction will increase. What is the formula? Hc by lambda is greater or equal to Eg. So if you simplify this equation, what we are going to get? Lambda less than or equal to Hc by Eg, where H is the appearance constant. C is the speed of the light, It is the, I can say, the forbidden gap energy, and lambda is the wavelength of the radiation of the electromagnetic radiation. Okay. If you know the Planck's constant, you know the speed of light, you simplify, substitute those values and if you simplify, we are going to get 1.24. When the lambda is less than or equal to 1.24 by Eg. If lambda is less than or equal to 1.24 by Eg, what is the maximum value? Lambda max is 1.24 by Eg. So what is the maximum lambda? 1.24 by Eg. So when lambda is less than lambda max, what is going to happen? Then this relation is satisfied. If this condition is satisfied, then what is going to happen? E is greater or equal to Eg. It means that whatever the energy that you are going to give the electron in the valence band, that energy is more than the band gap energy. So because of that, the electron will go from valence band to conduction band. So therefore, the free electron in conduction band will increase. So because of that, what is going to happen? The charge carriers are increasing, so conduction will increase. The conductivity will increase. Same thing again, the current will increase. Suppose if lambda is greater than lambda max, what is going to happen? This relation is volatile. The maximum value, 1.24 by Eg, but you are choosing the lambda which is more than this one. So nothing. This relation is volatile. So because of this, what is going to happen? It means that if you go for this value, we are going to get E less than Eg. If E less than Eg means we are giving energy which is lesser than forbidden gap energy. Definitely, the electron will not go from valence band to conduction band. It will not go. It will remain in its own position only. So because of that, the number of free carriers in the conduction band, it will not increase. It will remain as it is. It will remain as it is means the conduction will remain as it is, like previous one. What is the previous conductivity? Same will present now also. So signal will remain constant as it is. Okay. This is a very important thing here. Okay. So what is Eg? Eg is nothing but forbidden gap energy, which value is always equal to AC minus AV. What is AC? AC is nothing but minimum energy level in the case of the conduction band, and AV is the maximum energy level in the case of the valence band. What is AG? AG is called AC minus AV. What is AC? Minimum energy level in the case of the conduction band, and EV is the maximum energy level in the case of the valence band. Okay. So this one I already told you. The next one is, so Jn is equal to Q into Dn into Dn by dx, where Jn is for the current density of the electron, where Q is the charge of the electron, Dn is the diffusion coefficient of the electron, where Dn by dx is nothing but the concentration gradient of the electron with respect to distance. Okay. What is J2? J2 is equal to minus Q into Ap into dp by dx, where J2 is the current density of the holes, and minus Q is nothing but Q is the charge of the holes. Okay. And dp is the diffusion constant of the holes, and dp by dx is nothing but the concentration gradient of the holes with respect to distance. The concentration gradient of the of the poles with respect to distance. So both are having opposite nature. As if clearly both are either constant here or equal. The dn and dt are basically constant values. Okay? And this is called as the Pearson relationship. This is called as the Pearson relationship. This dt by dt is always equal to dn by dn is always equal to dt. So dt by dt is always equal to dn by dn is always equal to dt. What is dt? Diffusion constant of the ball. What is vp? The mobility of the ball. What is dn? Diffusion constant of the electron. What is vn? The mobility of the electron. Okay. So the ratio is always equal to constant. It is nothing but thermal voltage. It is always equal to thermal voltage. This is called as the Western relationship. And I already told you the mobility of the electron will be very, very higher when compared to the mobility of the ball. I already told this concept, right? And what is thermal voltage formula? It is equal to K into T by Q. Where V is the thermal voltage, K is the Boltzmann constant, and T is the temperature in Kelvin, and Q is the charge value, which is 1.6 10 to the power minus 90. Suppose if you keep the temperature of K in Kelvin, in case of T, it is substituted in Kelvin, and you know the value of K and V and the value of Q. Boltzmann constant value and K value, you know, to substitute simplify. Finally, you are going to get it is approximately equal to 26 millivolt. So therefore, the thermal voltage of a semiconductor is approximately equal to 26 millivolt at 10 Kelvin. Okay, that's a very, very important point to keep in mind. As T increases, Vt also increases. As T decreases, Vt also decreases because K and Q are constant values. Okay. So let me tell you regarding another concept, the crystal oscillator. So what's the meaning of the crystal oscillator? Basically, we are going to use this crystal oscillator in the case of the microprocessor. Basically, we use this one in the case of microprocessor in order to give the clock signals for the microprocessor to run. So, as for crystal oscillator, if you try to open the crystal oscillator, then you can say piezoelectric material. So, piezoelectric material is like a transducer which is going to convert the mechanical input to electrical output. So, basically, there are a lot of piezoelectric materials. Out of that, always we try to prefer the cost because it is a very cheap and also it is a very high mechanical strength, as well as it can available in nature in a very large quantity. So because of these series of we try to prefer the cost material in compared to any other piezoelectric material. So input we are going to give the mechanical vibrations like pressing and elongation. Okay. So because of that output we are going to get the electrical voltage. It is oscillating in nature. The electrical voltage that we are going to get is basically square wave shape we are going to get. Okay. If input is a crystal frequency, then what is the output? Clock frequency. Clock frequency is half of the crystal frequency. This one I already told you in case of the microprocessor. Okay. So clock frequency is always equal to half of the crystal frequency. So basically, for this crystal oscillator with the help of some electrical circuit, we try to give some mechanical vibrations for the crystal oscillator surface. So because of that, the piezoelectric material is going to vibrate like expansion and elongation. Expansion, compression will happen. So because of this output, we are going to get the electrical voltage. So input is the crystal frequency and output is the clock frequency. The clock frequency is equal to half of the crystal frequency. It's one of the I already told in my microprocessor classes. So what I will do, basically I will cut this crystal into two equal parts. Into two parts I will try to cut it and I will try to keep across the metal place. So if you try to draw the equivalent circuit diagram, then we are going to get like this. So this is a one piece electrical model and this is the other piece electrical model. Okay. So this is the overall crystal oscillator circuit. Okay. So this is a series RLC circuit and the capacitor. So this is the LS, RSM, CS. This is the CT. So this is the overall electrical circuit model of the crystal oscillator. So for this we are going to have the two resonant frequencies. So for the circuit we are going to have the two resonant frequencies. What are those? FS and FP. FS is called the series resonant frequency and FP is called the all resonant frequency. So directly remember this expression, which is FS is equal to 1 by 2 pi under root over LSCS and FP is equal to 1 by 2 pi under root over LS into CS CV by CS plus C2. Okay. I request you to remember these formulas. Okay. So if you see clearly here, CS and C2. So what's the meaning of this one? CS into CV by CS plus C2. So basically, what's the meaning of this one? Like I can say that, so you know this formula, right? Whenever two resistors are in parallel, what is going to happen? R1 into R2 by R1 plus R2. So this net resistance will be always lesser than the minimum of individual R1 and R2. Okay. So therefore, whenever the two resistors are in parallel, I can say that what is the net resistance? R1 into R2 by R1 plus R2. So the second resistance will be always lesser than the minimum of the individual. In the same fashion, same formula is there. CS into CV by CS plus CV. So what is the meaning of this one? This net capacitance is also lesser than the individual. So therefore, this net capacitance is also lesser than the individual. It is lesser CP. So it is lesser than a minimum of all these things. It is lesser than the minimum of these three things. So whatever this value you are going to get, it is lesser than the CS always. It is lesser than the CS only always. So because of this, what is going to happen? This denominator will be very, very less. Because this value is lesser compared to this value. So because of this value, this denominator will be very, very less. So the ratio will be very, very higher. So that is the reason FP will be greater than the FS. Or you can say FS is less than FP. So therefore, the second resonant frequency will be always lesser than the other resonant frequency in the case of the crystal oscillator. As you can see clearly, whenever you try to keep the resistors in parallel, so what you are going to do around the circle, that is a net resistance, it will be always lesser than the minimum of the individual resistance. In the same fashion also, this formula is also present. So therefore, this equivalent capacitance value will be minimum than the individual capacitance. So this value will be minimum out of the, it will be always lesser than the minimum of the individual capacitance. So definitely this value is lesser than CS. So if this value is less than CS, so denominator is always lesser. So overall value will become very higher. So therefore, FP is greater than FS, or you can say FS is less than FP. So in the case of crystal oscillator frequency, in the case of crystal oscillator, we have two frequencies, two resonant frequencies. One is the series resonant frequency, which is FS, and FP is the parallel resonant frequency. And the relation is always FS is less than FP. Okay, this is very, very important thing you have to remember. So finally, let me try to give you a graph of the semiconductor in the case of intrinsic semiconductor. This is basically intrinsic. So to the idea, this is basically for the intrinsic. Okay? Just give me a second. Let me write this one. This is for the intrinsic. Whatever the graphs that I am going to teach you, these are for the intrinsic semiconductor. Okay? These are for the intrinsic semiconductor. So I am going to draw the graph between the concentration of the charged particles with respect to temperature. So already told you, pressure of N is very proportional to P2. If T is 0, Na is also 0. Okay. If T increases, Na also increases. So like this I can draw. Approximately I can draw the graph like this. Okay. So if T increases, Na is also increases. Sometimes they can use either C also they will use. Which they will try to use. Either you can use Na or C. Na is nothing but concentration, or you can say C also concentration. Means these one number charge particles they are going to present from the unit volume. Okay. So this is what the intrinsic semiconductor. Because Na is very proportional to Q. As T is equal to 0 Kelvin, Na is also 0. Okay. As T increases, Na is also going to increase. Yes, the amount of charged particles per unit volume will increase. Okay, as you can see clearly here. So, as you can see clearly, as temperature increases, the concentration of the charged particles also going to get increases in the case of the intrinsic semiconductor. But if you want to draw the graph between them, mobility with respect to temperature, see, when you try to increase the temperature, yes, the mobility will also increase at a certain temperature. So you can see clearly from this graph. So whenever you try to increase the temperature, yes, up to certain temperature, the mobility will increase. But after that, it will decrease. So this is for the electron as well as hole also, same person. The mobility is available, it is for both the electron as well as hole. So at a certain temperature, yes, the mobility will increase. But after that, it will decrease. As you can see clearly from this picture. Okay. The C is the concentration. These will the charge particles are present per unit volume. When U is the mobility of a electron or mobility of the hole. And this temperature is always measured in terms of Kelvin. Okay. And I already told one important point just now previously. Whenever you try to keep the intrinsic semiconductor in the case of the 0 Kelvin, it is going to act like a purely insulator because the charge carriers are 0. Total charge carriers are 0. Whereas if you try to keep the excited semiconductor, whether it is a p-type or n-type, in the case of the 0 Kelvin temperature, still there are few charge carriers. So because of that, it is going to act like a conductor. I have already explained the proof also. I have already explained. Okay. So this graph is for the intrinsic. That is the reason. Even if P is equal to 0 Kelvin, the intrinsic concentration is equal to 0. Okay, as you can see clearly here. So now what I will do? See, basically here I have drawn the graph between Na and P. Okay, you can basically apply this concept for both the intrinsic concentration eccentric also, because I am telling you regarding the Na only. I am telling you only regarding the Na. So if you are applying only for Na, so you can apply for both intrinsic concentration eccentric also. So let me write this down. So you can apply this concept for both the intrinsic as well as eccentric, because here I have told you in the y-axis we are taking the Na. We are taking the value of Na, but not the value of N or P. I am not taking the value of N or P. Therefore, I can apply this concept for both the intrinsic as well as eccentric. If you try to apply this concept for the p-type and n-type, then if T is equal to 0, Na is 0. If N and P are not equal to 0, I already told you. So because of that, what is going to happen? some free carriers are already present, it is going to act like a conductor. Okay, that is the point we want to take into account. So that is the reason. And in this semiconductor, when you try to keep it at the 0 Kelvin temperature, it is going to act like a excitor. Whereas if you try to keep the excited semiconductor, that is a P type or N type, in the we can say at 0 Kelvin temperature, it is going to act like a conductor. I already explained the proof also. So now, let me try to explain another cause, which is the drift velocity of the electron. Okay, so this is the graph between the drift velocity as well as the electric field. So I am going to show you the graph between the drift velocity as well as electric field. I am trying to show you the graph here. So you can see clearly this is the drift velocity of the electron and this is the electric field. So the graph here is going to get like this. So after certain range of electric field, the drift velocity increases linearly. Okay, as E increases, V also increases linearly. But after some certain time, it will become saturation. It will become saturation. So you can see clearly, after certain amount of electric field, as electric field increases, the drift velocity of the electron will increase. Okay, linear fashion. But after that, it will remain constant. So why does like this? Let me tell you. Okay, see, as you can see clearly from this picture, after certain digit of electric field, as electric field increases, the drift velocity increases. But after that, even though you try to increase the electric field, the drift velocity is almost constant. It is got saturated. Okay. So if I take two regions, we have two regions, the linear region and this is saturation region. As you can see clearly, this is the linear region and this is saturation region. So you know the basic formula. Vd is equal to mu into E. So you know Vd is equal to mu into E. Here Vd and here both are directly proportional. So what is the meaning of this term? Mu is constant. So mu is equal to constant. So therefore Vd is directly proportional to E. Whereas here if you see clearly, what is going to happen? Vd is constant, but E is increasing. Then what is the meaning of mu? Mu should decrease because Vd is equal to mu into E. If Vd is constant and E is increasing, definitely mu should decrease. If increasing and decreasing, then only we are going to be constant. Therefore, we can see in this case, as the value of P increases, mu will decrease. Then only the part is equal to constant, which is Vd is constant. Whereas in this case, we can say that here mu is constant. So because of this, V is directly proportional to E. Here mu is decreasing. So because of that reason, Vd is constant. So therefore, you can say clearly, Vd is equal to mu into E. Where Vd is a drift velocity, mu is the mobility, and E is electric field. So for certain value of electric field, as E increases, Vd also increases. But after that, even though you try to increase the value of electric field, the drift velocity is almost constant because of the saturation. Or you can say this becomes saturated. Okay. Here, because of linear region, mu is constant, so therefore Vd is very proportional. Whereas here, when you try to increase the value of electric field, Vd is constant, so therefore as Vd is constant and E is increasing, so definitely mu should decrease. Then only the point is equal to constant. Therefore in this region, the mobility is decreasing. So therefore I can say finally, after certain range of electric field, if you try to increase the value of electric field, the drift velocity of the electron will increase. But after that, it will remain constant because of the saturation effect. Okay. The next concept is about the Fermi level. So Fermi level, I'll try to explain. What is the meaning of the Fermi level? Fermi level means it is nothing but here at normal temperature, at normal temperature, 50% of the electrons, sometimes they may available 50. So there is a property of some of the electrons may available in the Fermi level. Okay? So listen carefully. At a room temperature, there is a 50% probability that some of the electrons may available in this level, that is also Fermi energy level. So what's the definition of Fermi energy level? Say at certain room temperature, okay? At certain room temperature, there is a 50% probability that some of the electrons may available in this energy level, that is also Fermi energy level. Okay? So let me tell you where it is lying for the P type as well as N type. So basically we have two bands. One is the valence band and the other is the transition band. In the case of valence band, only we have holes. Holes are going present only in the case of the valence band and the valence band electrons. So basically we have valence band electrons as well as we can say the holes are going to present only in the case of valence band, whereas the free electrons are going to present only in the case of conduction band. There is nothing like holes here. We can't see any hole in the conduction band. Only we can see the free electrons. Whereas here, in the case of valence band, we can see the holes as well as the valence band electrons. Therefore, I can say that in the case of valence band, we can see only the holes as well as the valence band electrons. Whereas in the conduction band, we can see only the electrons, free electrons. Okay, but not any holes. Okay. So In the case of P type of semiconductor, the Fermi energy level is very closer to valence band. So you can see clearly from this picture. In the case of P type of semiconductor, the Fermi energy level is very closer to valence band. Whereas in the case of the N type of semiconductor, the Fermi energy level is very closer to conduction band. So you request you to keep this one here now. So in the case of the N type of semiconductor, the Fermi energy level is very closer to conduction band. So how to remember this shortcut? Let me tell you. So let me tell you how to remember this one. Okay. So how to remember this one? Let me tell you a shortcut here. So try to assume like this. Try to assume a diode in this fashion. This is basically anode. This is cathode. But here I will assume this is a P. Here this is a N. Okay. I'll try to assume like this. Then here P is here, right? So P here means the P here means the Fermi energy level is downward. Okay. N is here. So therefore the Fermi energy level is upward. Okay. Therefore for the P type of semiconductor, the Fermi energy level is near the valence band, and for the N type of semiconductor, the Fermi energy level is near the conduction band. So you can see clearly because I have drawn the diode in this fashion. Okay, so this is basically anode and this is cathode. So here I will try to assume this is P and this is N. So P semiconductor and N semiconductor. You know basically what is it? P and N. So let me draw the picture here. So this is basically a P type of semiconductor. This is an N type of semiconductor. Okay. So I can draw like this. This is actual symbol diagram. But if I try to draw a representation, we are going to get like this one. I can write this is P. I can write this is cathode means I can write N, right? So I can write the anode cathode means P and N. I can write like this. So this is downward. P is down and N is up. So P is down and N is up. So therefore, Fermi energy level is near the valence band in the case of the P type of semiconductor. And the Fermi energy level is near the conduction band in the case of the N type of semiconductor. As you can see, N is up. Fermi energy level is up. P type means the Fermi energy level is down. P is down, right? So Fermi energy is also down. N is up. So Fermi energy level is also up. Shortcut to remember. This is a P and this is a N. So P is downward. So Fermi energy level is also downward. Okay. Where N is up. So Fermi energy level is also up. So therefore, I can say that finally the Fermi energy level is near the valence band in the case of P type of semiconductor and is near the conduction band in the case of the N type of semiconductor. Same thing I have to do. So this is a diode. It's actually P junction and N junction. Second hand is a P, this is a N. So P is down, N is up. So P is down means Fermi level is down. It is near the valence band. Means P is down means Fermi energy level is also down. Where N is up means the Fermi energy level is also up. So what is here? Here P is down. So P is down means Fermi energy level is also down. Okay? Here N is up means Fermi energy level is up. Up. In up means we know conduction band. Down means we know valence band. So shortcut remember. So finally I will tell you the shortcut here. Basically I have drawn the PN junction. Okay? So I have drawn a diode symbol also like that. So down is P, N is up. Down is P means Fermi energy level is also down. Okay? N is up means Fermi energy level is also up. So therefore, at top you will have the conduction band and at down you will have the valence band. So therefore, for the P type of semiconductor, the Fermi energy level is near the valence band, and for the N type of semiconductor, the Fermi energy level is near the conduction band. So finally, I can say that for the P type of semiconductor, the Fermi energy level is near the valence band, and for the N type of semiconductor, the Fermi energy level is near the conduction band. Okay, this is a very important thing that you have to keep in your mind. Definitely, you can get additional question from this concept. This is the same thing I have told you, but let me try to finally summarize this concept. What is the temperature coefficient for resistance for different types of materials? Okay, you have three types of materials: conductor, semiconductor, and insulator. Okay, so conductors are always going to have the opposite of the coefficient for resistance. Means as temperature increases, the resistance will increase. So because of this, the current will decrease. Whereas in the case of the semiconductor, we have two things based on the type of the doping. We have highly doping and the light doping. Suppose if we are going for light doping, it will become light doped semiconductor. If you are going for the highly doping, it will become the highly doped semiconductor. So highly doped semiconductor is going to behave like it is going to have the lowest temperature coefficient for resistance. Means as temperature increases, the resistance will increase. So because of that, current will decrease. Whereas the light doped semiconductor, so whereas the light doped semiconductor is going to have the very temperature coefficient of resistance. So because of this, as temperature increases, the resistance will decrease. Current will increase. Okay. Whereas the incentive is going to have the negative degree coefficient for resistance. So therefore, as surgery increases, the resistance will decrease. So therefore, that quantity will increase, as you can see clearly from this picture. And one more thing is always, you can see clearly, so based on the type of doping, the semiconductors can have either positive coefficient of resistance or the negative coefficient of resistance. It's a very, very important statement always, so you have to keep in your mind. So based on the type of doping, the semiconductors can have either a positive coefficient of resistance or the negative coefficient of resistance. Okay? So based on the type of the doping, so based on the type of the doping, semiconductors can have either a positive temperature coefficient of resistance or the negative temperature coefficient of resistance. Now to remember shortcut, here high means positive, low means negative. Okay, here high means positive, okay, low means negative. Okay, and up to both are upper positive, down to are negative. So upper to first two are positive, next two are negative. Okay, so first two are positive, next two are negative. Shortcut remember. So high means positive, low means negative. Okay. Now already told up to are the positive, down to are the negative. Now already told you what is the example of the light dope semiconductor, it is thermistor. Now already told you the best example of the light dope semiconductor is the thermistor. Now already what is the best example of the high dope semiconductor is the sense system. So suppose if I want to tell you the concept, what will happen in listen carefully. I will list all concept. Okay. So in the case of thermistor, it is a light dope semiconductor. So whenever you try to increase the temperature, what is going to happen? The charge pairs are going to go from the valence band to conduction band. So definitely the charge pairs will increase. So whenever charge pairs increases, the conductivity will increase. So therefore the resistance decreases. Whereas in the case of high dope semiconductor, if you try to increase the temperature, what is going to happen? When you try to increase the temperature between the charges, yes, the charges are more, but what is going to happen is the collisions will happen. So because of collisions, the overall charge carriers value will decrease. Only some will remain, but the remaining thing will go damage because of the collisions. So only few are going to get remain. If few are going to remain means the probability is very, very less. So therefore the resistance is very, very higher. Because of higher though, there will be a lot of collisions between the charge particles. So because of that, overall value will decrease. So overall charge particles are very, very less. So therefore the quantity is very, very less and the resistance will be very, very higher. It is a very small concept, but it tell you why it is like this. Different from I don't know, we don't have to only. But if you can remember by the help of shortcut also these things. Finally I can say, so based on the type of doping, the semiconductors can have different values to the whether it can have the positive coefficient of resistance or the negative coefficient of resistance. So based on the type of doping, the semiconductor can have either positive temperature coefficient for resistance or the negative temperature coefficient for resistance. Okay. So finally, this is the very final concept here of this semiconductors. Some important points I will try to explain. Okay, I am using the Hall coefficient RH. We can figure out both the sign as well as charge and the density of the charge carriers. I have already told this point here. I think let me show you. Here I have already told you value of RH. So I have already told you just by knowing the value of RH, whether we can figure out the charge density, and it also its sign also you can figure out. For only told for electrons it's a negative, and for only it's a positive. So therefore, and you can even see signs also positive and negative. So therefore you can get the value of sign as well as the charge density also. So therefore, whenever you try to figure out the value of the Hall coefficient, you can also figure out it's a sign as well as charge density. Means this one number of charge particles are going to present per unit volume. So just by measuring the value of the Hall coefficient, you can figure out the its sign as well as the charge density. Okay, that is what I have already told you. So by measuring the Hall coefficient RH, we can figure out both the sign as well as the density of the charge carriers. For electron it's a negative, for holes it is positive. Okay, so how many number of charge particles which are present per unit volume also we can measure. I have already told you. And with this point also I have already told you, this Hall voltage or the Hall coefficient is positive for the P type of semiconductor, and is negative for both the N type of semiconductor as well as intrinsic semiconductor. So this will also I have already explained. So therefore you can say that the Hall voltage or the Hall coefficient, it is positive for the P type of semiconductor, and is negative for the N type of semiconductor as well as the intrinsic semiconductor. So finally, I can say the all voltage or the all coefficient can be either positive for the p type of semiconductor, it can be negative for the both the n type of semiconductor as well as the intrinsic semiconductor. We can see signs also. We can see the signs also. For the p type it is positive, for n type and intrinsic it is negative. Okay. The next point is gold is basically it is used as a recombination agent. Why means whenever we use the gold in the case of the semiconductors, so because of this, what is going to happen is a recombination. So electrons from the conduction band will come very faster. If in this amount of time they will come very faster to the valence band. So because of that, electron hole pair is disappear. So that is the reason we say it is using as a recombination agent. It can make the recombination to occur very faster. In the less time, the electron hole pair is going to disappear. Okay. So whenever the electron is coming from conduction band to valence band, definitely it is going to liberate the energy. Okay. So then now the next concept is here. Next point is holes present only in the case of the valence band and the free electrons are going to present only in the case of the conduction band. Only two holes are going to present only in the case of the valence band, whereas the free electrons will present only in the case of the conduction band. This one I already told you. So holes, whenever an electron is going from valence band to conduction band, then only the hole is or the vacancy is located in the valence band. So definitely holes will present only in the case of the valence band. We will never see any hole in the conduction band. Always we will see the holes only in the case of the valence band. And the free electrons are going to present in the conduction band. Okay. So now the next thing is here. An electron in the valence band can be transferred by the field only when empty energy levels are available in the valence band. So what's the meaning of this one? Suppose, let me give you a small example. Suppose I'll take like this one. Suppose two electrons there in the valence band. So because I have given energy, so now they have went to the conduction band. Definitely some holes are created, some vacancies, two vacancies are going to create in the valence band. You can try to explain this concept here. So this is the conduction band and this is the valence band. So let me assume initially I have 4 electrons, okay? I have 4 electrons, okay? Initially I have 4 electrons. Suppose I have given some energy to this electron. So one electron is going from valence band to conduction band. Suppose this electron is going from valence to conduction. And what is going to happen? This electron will go to this position. So now there is a vacancy, right? So there is a vacancy here. So there is a vacancy in the valence band. So now it is nothing but it is going to become a hole. It is going to become a hole. So let me show you the other color. So let me show you the other color. Yes, other here. So this is a hole. Okay. So whenever an electron is going from valence band to conduction band, definitely the whole vacancy is going to be valence band. Okay. I am going to be the circle. Okay. Suppose now what I will do, I will apply some electric field for this semiconductor. Then what is going to happen? Yes, these electrons are also going to get transferred, and also this valence band electrons will accelerate because there is a hole, right? So this will go from here to here. So now this vacancy is filled. I will show you this vacancy is filled. Okay, or this vacancy is open. This vacancy is open. So this is like this one. Again, what we will do? This electron will go here. Now what is going to happen? I will show you. So like this again, new vacancy like this one. So you can see clearly here. Whenever we try to use the thermal energy for the semiconductor, then of course will go from valence band to conduction band. Yes. So here I am showing one electron is going from valence band to conduction band. So now definitely one hole is going to basically figured in the valence band. Suppose if I give the electric field, then this electron will accelerate, this conduction band electrons will accelerate, and also this valence band electron will also accelerate because they will go from here to here in order to fill this vacancy. So when it goes to fill this vacancy, again here this is a new vacancy created here. So here this one. Again this electron will try to move from here to here in order to fill this vacancy. Again a new vacancy is created. So you are going to get like this one. So therefore the valence band electrons will accelerate only when there is some vacancy or when there is some empty energy levels. So this one is nothing but vacancy or empty energy level. Suppose if it is not available, then the valence band electrons will never accelerate. Okay? If holes are created, if holes are present, if some vacancy is present in the valence band, then only the valence band electrons will accelerate. Otherwise, it will never accelerate. Suppose if there is no hole, in the valence band, suppose if we think like this, if there is no hole in the valence band, even though you try to give the electric field, this valence band electrons will never accelerate. Okay. So whenever there is a hole for vehicles in the valence band, then only the valence band electrons will accelerate. Otherwise, they will never accelerate. Okay, this is what I'm telling you. Very, very important concept. Always you have to remember. So therefore, I can say that whenever there are some empty energy levels which are nothing but holes, okay, then only the valence band electrons will accelerate if you try to give the electric field. Suppose if there are no vacancies, if there are no holes, if there are no empty energy levels, even though you try to give the electric field, the valence band electrons will never accelerate. Okay. So an electron in the valence band can be accelerated by field only when empty energy levels are available in the valence band. Means if whenever the vacancy, whenever the hole, whenever the empty energy levels, if they are available in the valence band, then only you can accelerate the valence band electrons. Otherwise, if there are no vacancy, if there are no empty energy levels, if there are no holes in the valence band, then it cannot accelerate the valence band electrons even though you try to give the electric field. So this is what I am trying to tell you. Okay, so this is a very, very important point. But the conventional electrons with energy accelerate even though there are no holes here, because holes will never present in the connection band. Just to give the electric field, they will always accelerate. So this electric field, this free electrons in the conventional band, they will always accelerate. Even though you try to give the electric field, they will always accelerate. Okay, as you can see clearly here. This concept also I already told you. Okay. An electron in the valence band can be accelerated by electric field only when the empty energy levels are available in the valence band. If the empty energy levels of the holes or the vacancies, if they are available in the valence band, then only the electrons in the valence band will be accelerated by the electric field. Otherwise, if there are no empty energy levels, if there are no holes, or if there are no empty energy levels, or no holes available in the valence band, if you try to give the electric field, the electrons in the valence band will never accelerate. Okay. So, impurities are always neutral. I already told you one of the impurities, group 3 elements and group 5 elements, these are the impurities. So, if you take the group 3 elements, suppose like to tell you group 3 elements like boron. So, boron atomic number is 5. So, it will have 5 electrons in the outer shell, in the orbits, and it will have 5 electrons, it will have 5 protons in the nucleus. So, number of protons is equal to number of protons. So, boron is having electrical charge of 0. So, nucleus. So I can say intrinsic are always physically neutral. Okay, it's a very important point. One more point is here. I already told you that whenever you try to keep the intrinsic semiconductor in the 0 Kelvin temperature, it is going to act like acid. I already told you this concept so many number of times. So whenever you try to keep the intrinsic semiconductor in a 0 Kelvin temperature, it is going to act like a fully acid. I already told you because at this condition, the Na value is equal to 0. If Na is equal to 0, by default N is equal to P is equal to 0. Means there are no free charge carriers. So because of this reason, it is going to act like an insulator. But when you try to keep the eccentric semiconductor connector in the case of 0 Kelvin temperature, it is going to be a conductor. Why? Because I already told you, even though at 0 Kelvin temperature, yes, Na value is equal to 0. Na value is equal to 0, but the value of P and N are not equal to 0. I have already shown you with the help of equations also. I have already told you. So in the case of P-type semiconductor, even though Na is equal to 0, P value is not equal to 0. In the case of N-type semiconductor, even though Na is equal to 0, but N is not equal to 0. So because of these reasons, that even at 0 Kelvin temperature, semiconductor, the free charge carriers are available. So because of this reason, it is going to act like a conductor. Okay. So finally, last point here of this lecture, which is say for a silicon. So for the silicon, what is the band gap energy? It is 1.1 electron volt for a temperature of 300 Kelvin. Okay. And its value is equal to 0.78 electron volt for germanium at temperature of 300 Kelvin. So these values are also very much important. Definitely they will ask in the examinations. So for silicon at temperature of 300 Kelvin, we can say that the band gap energy is 1.1 electron volt. And for germanium at temperature of 300 Kelvin, its value is Eg value is 0.78 electron volt. Okay. So if you see, if you compare the voltage values, silicon is having a more Eg when compared to germanium. Okay. And what's the meaning of 1 electron volt, which is 1.6 10 to the power of minus 90 joules. Basically, you can write the energy in terms of joules, or you can write in terms of electron volt also. You can write. And what's one electron volt, which is 1.6 10 to the power of minus 90 joules. What is Eg? It is the Coulomb gap energy. It is a simply its value is equal to AC minus CV. What is AC? I already told you it is I can say minimum energy level in the case of the conversion layer, and what is EV? Maximum energy level in the case of the valence wire. Okay, so very important thing. So always remember these two values. For silicon, at a temperature of 300 Kelvin, its value is equal to 1.1 electron volt, and for the germanium, at a temperature of 300 Kelvin, let's say 300 Kelvin, its value is equal to 0.7 electron volt. 1 electron volt is equal to 1.6 10 to the power of minus 9 joules. So basically, here I am giving some of the important points or important concepts. Quick revision. It's not a brief revision, but only a small amount of quick revision I am giving. So some people who have already studied this subject, they can get good advantage for this quick revision. So right there, we have understood these concepts. So if you like the content of our channel, then please to like, share and subscribe to the channel. And don't forget to press the bell icon button. So whenever I upload a new video, direct notes comes from my If any information in our lectures, then please put in the comment section. We will definitely include all those lectures in the coming lectures. Thank you so much for watching this lecture. Please for it. Bye bye.